Hi everyone. So in the last video we have seen the forward propagation. Today in this video we will look at the backward propagation. So this is where you compute the gradients, you derive the loss function with respect to the biases and the weights, and maybe we should remind ourselves on what we did before. This is much more like the continuation of the previous video. So in the previous video we had layer 1, right, and layer 2 and layer 3. In layer 1 we had A1 and Z1. We also had A2, Z2 in the second layer, then A3, Z3 in the third layer, and we computed the three to be, the predictions of the neural network. The input, we called it a 0, or you can call it X, had a dimension of BS by F, and the layer 1 had a dimension of BS by F1. Sorry, both A1 and A2 had a dimension of BS by F1. A2 and Z2 had a dimension of BS by F2. BS was the batch size. F3 similarly. Alright, and we also had the weights of W1, weight of the first layer, the weight of the second layer, also the weight of the third layer, had a dimension of F by F1 by F. This was F2. I'm writing these weights because we need them in the computations that we're going to do in the video here. Alright, so what happens is that in each layer of backpropagation, you compute DWL, layer L. We also compute DBL, so derivative of the loss function with respect to bias of layer L. Then the AL minus 1, the ZL in each layer of backpropagation. Okay, DWL is 1 divided by BS. By the way, I got these formulas from Andrew Ng's course. And there might be slight variations in the dimensions, but it doesn't matter, you end up with the same results. And the DWL is 1 divided by BS. The ZL transpose AL minus 1, this is 1 divided by BS. Then summation 1 from 1 to BS of DZ LI. Then this is DZ LWL, and this is DAL. This is only applicable when we use the nonlinear functions like ReLU. Then element wise product of that ReLU, for example, with respect to ZL. Okay, these are the formulas that we use, and the loss function that we are going to use can be achieved in Pytorch using Pytorch.bcc, Pytorch.binary cross entropy. And the formula for binary cross entropy is this. and y log of y hat, this is the target, plus 1 minus y I log of 1 minus y hat. So this is the formula for binary cross entropy. So this is the information that we need to start back propagation. So let's get started. So in here, before we started from the left, so in here we start from the right. So we start from layer 3. The first thing that you need to do is compute dA3. This is the first thing that you really need to do, which is the derivative of the loss function with respect to your prediction. And it is this. Using calculus. And this formula depends on the loss function. So the derivative of the loss function with respect to A3 or the prediction is this. This is the formula. And when you apply the formula, you put in your values y, a, and where do you get a? A3, we already have A3. You know your target. You end up with something, a tensor of dimension bs by f3. Okay. So, but we need to ask ourselves, did we apply any ReLU in this layer? We did not apply any ReLU, so we are just going to say dz3 is dA3. If we had applied a ReLU, for example, dz3 will need to be computed using this formula. Okay, so but you don't need to worry about it because we have not used it. I make this intentionally, did not use it to simplify everything. And yes, so we know so now we have dA3 and dz3. The next thing that we need to do is to compute dw3 using the formula here. We know that this is much like a scalar, so the formula says get dzl, which is dz3, we're in layer 3, dz3 transpose, then a2, al minus 1. Do we have this? Yes, we have. We already have them. We computed them. dz3 is actually dA3. Then we take the transpose, then it becomes f3bs. A2, we have A2. A2 is bsf2. Alright, and when you multiply them, you end up with something like this, f3, f2. Okay, so far so good. Then we need to compute dp3. How do you compute it? We have the formula. We should not forget to multiply. Okay, this is a tensor, then you multiply it by 1 over bs, but the dimension will not change. Okay, so db3 says take each column. What the summation here means is take each column and sum it up. So at the end, you are going to have one row and multiple columns. So let me make it clear. So db3, the formula here says take dz3 maybe dz3 was this, I'm just saying, then sum up this things, sum up this, sum up this, and sum up this, then you end up with something like this. This is the summation of this 3. This is what the formula here is saying. So which means you end up with something 1 by f what, let's see, f3 actually, because the dimension will depend on dz3, and dz3 had a dimension of bs by f3, so we are squeezing kind of the batch. All right, so far so good. Let's continue. Then we need to compute, we need to use this formula now. The formula here says dA2, we're in layer 3, so dA2, how do you compute it? Use dz3 w3. What is dz3? dz3 has a dimension of bs by f3. w3 had a dimension of f2, right? I think this should be f3. I think I made a mistake here. Yeah, w3 had dimension of f3 by f2, and you end up with a tensor of dimension bs by f2. All right, now we are done with the last layer. We move on to layer 2. We did not apply any ReLU or maybe sigmoid, so we're just going to say dz2 is dA2. Why did we say this? Because first of all, we need dz2, and we have already computed dA2. Next, we need to compute dw2, which is 1 divided by bs of what? What is it? dz2. dz2 had a dimension of bs by f2. We take the transpose, then multiplied by a1, which has a dimension of what? bs by f1. So I have to rewrite this to make it clear. bs Alright, so the transpose of this is f2 bs by f1. We end up with something like this, f2 by f1. Then you multiply by 1 divided by bs. In this case, we had bs was actually 1, so even if it is not 1, this dimension will not change of dw2. Okay, so let's move on to db2. Similarly, just here like this, db2 will have, db2 relies on what? dz2, and dz2 had a dimension of bs, because dz2 is the same as dA2, has a dimension of f2. So just like here, it's going to have dimension of something like this. This is what the formula is saying. Okay, then the A1. What is the A1? Well, the A1 says DZL. Actually, let me write it like this. DZL, which is 2 times W 2. What is dz2? The dimension of dz2, bs by f2. w2 was what? This f2 by f1. Then you end up with a tensor of bs by what? f1. Well, don't forget again, this is a tensor, the dimension of a tensor. Okay, then we move on to the last layer. But did you notice something? dw2 has the same dimension as the w2, and dw3 has the same dimension with w2. This is very important when applying gradient descent because they have to have the same dimension. Alright, the last layer. In here we start by saying dz1 is dA1, and maybe I should write they both have a dimension of bs by f1. Okay, then dw1 is 1 divided by bs, which is 1, multiplied by a tensor. What is dw1? Let's go back. It is dz1 transpose. What is dz1? Well, dz1 is this. The transpose is f1 by bs. f1 by bs multiplied by a0. What is a0? A0 is actually this. So input bs by f. When you multiply, you end up with a tensor of dimension f1 by f. Alright, let's get to db1. Just like in here, db1 is 1 by f1. Then finally, we don't need to. Technically, I'm not sure if you need to, but you can compute dA0. dA0 is what? dz1 has a dimension of what? bs by f1. Then w1 has a dimension of f1 by what? f, and with tensor of dimension bs by f. This is a tensor, and notice that dw1 has the same dimension as w1. Okay, so in the next video we will look at for the gradient descent to update the weight to become better, to update this weight in the next video. Thanks for watching.